We're now going to cover some more definitions relating to graph theory, including complete graph and bipartite graph. If a graph is simple, meaning that it contains no multiple edges and no loops, and every vertex is directly connected to every other vertex by an edge, this is called a complete graph. So complete graphs contain every possible edge. I'm going to ask you to pause the slide in a minute and draw all of the complete graphs up to and including the one with 6 vertices, and count the number of edges needed to make a complete graph. I'm just going to start you off with the first 2. So the complete graph with 1 vertex contains no edges because there's only 1 vertex. It doesn't need joining to any others. And the complete graph with 2 vertices contains 2 vertices joined by 1 edge, as shown. So pause the slide now and continue the pattern, joining every vertex to every other vertex, up to and including 6. So the complete graph on 3 edges is shown below. This needs 3 edges to join the 3 vertices to each other. The complete graph with 4 vertices requires 6 edges in order for every vertex to be connected to every other vertex. For 5 vertices, we need 10 edges. And for a complete graph on 6 vertices, we need 15 edges. Now, there is a formula for this. A complete graph with n vertices. The notation for this is Kn. So Kn means a complete graph with n vertices. For example, the complete graph with 5 vertices will be written as K5. The formula for the number of edges, if you consider that in a complete graph, each of the n vertices needs to be connected to every other vertex. This means that each vertex will have a connection with n-1 other vertices. So there will be n times n-1 connections. However, this will then count each edge twice because it will count it from each end. So we'll then need to divide the number by 2. Therefore, the complete graph with n vertices requires a half n-1 edges in order to complete it. So we can just confirm that. If we confirm it with the case for 6, a half of 6 times 5, that gives us 15. The next definition we're going to look at is the complement of a graph. The complement of a graph contains the edges that are needed to be added to the original graph to make that graph complete. So for example, with this graph, which edges will be needed to make the graph complete? So we would need the edges in red to complete the graph. Notice that the complement still uses all of the vertices of the original graph. Adding these 2 graphs together will make the complete graph with 5 vertices. The next definition is for a bipartite graph. Bipartite graphs link 2 independent groups of vertices. In this example, we've got group 1 containing vertices A, B and C, and group 2 containing vertices X and Y. Edges can only join vertices from group 1 to group 2, as shown. Edges cannot join 2 vertices within the same group. A use for bipartite graphs might be in a matching problem where group 1 would represent people, group 2 would represent jobs that needed to be allocated. A bipartite graph can be complete if all of the possible edges between the 2 groups are drawn in. The definition of KMN is a complete bipartite graph with m vertices in one group and n vertices in the other. Pause the slide now and draw the complete bipartite graph K42. So K42 contains 4 vertices in one group, 2 vertices in the other. If you systematically work your way down one group, drawing in all of the possible edges to the other group, you will end up with the complete graph. Now consider the complete bipartite graph KMN with M vertices in one group and N vertices in the other. Pause the slide and consider how many vertices that graph would contain and how many edges it would contain. So KMN would have M plus N vertices, just by adding together the two numbers of vertices. And because every vertex in one group has an edge with every vertex in the other group, we would need MN edges. I'd now like you to consider whether this graph would be bipartite. You may need to redraw it. You can move the vertices around on the page, but you cannot disconnect any of the edges in order to do so. So initially this graph doesn't look bipartite because the vertices haven't been drawn in two distinct groups. However, if we consider each alternate vertex here, you may do this by colouring them in different colours, like this. We can see that they could be drawn in this alternative way here. It's now clear to see that the graph is bipartite because we now have two distinct groups with edges travelling between them. So if you were trying to decide whether the graph was bipartite, colouring the vertices in different colours and checking that no vertices of the same colour will join to each other is an efficient way of doing that.